Okay, thank you for that introduction. And I'm very happy to be here and give you this lecture about transformer explainability, which is also the topic of my two recent papers. So as I was introduced, my name is Hila, and I'm a master's student at the Deep Learning Lab supervised by Professor Leo Wolf. I did my bachelor's degree at the Technion, and I authored two papers on transformer explainability. So let's begin by motivation. Why do we care about transformers? So as we heard from two speakers before, transformers appeared first in Attention Is All You Need in 2017, and they took the NLP world by storm. What does it mean that they took the NLP world by storm? Attention Is All You Need shows that transformers are able to outperform the previous state-of-the-art by a very significant gap, while being also more efficient. So what is this magical transformer? What is it built on? It's basically built on a very simple mechanism, and I'm going to focus on the self-attention mechanism. So when we read text, for example, the text that we see here, the cat sat on the mat, intuitively and without even thinking about it, our brain makes connections between the words in the sentence. For example, the word the is quite ambiguous and has no meaning without a context. So we know that the first the in the sentence refers to the word cat. So what the attention mechanism does is basically calculate similarity scores between the words, and then we integrate the embedding of the relevant words into the other words. Meaning, if we know that the word cat is related to the word the, then the attention mechanism will embed some of the word cat into the word the. So each word contains embeddings of the other relevant words in the sentence. Basically, a very simple and very intuitive mechanism. After we got Attention Is All You Need, we had BERT, which further extended the revolution of transformers in NLP. What BERT did was say, hey, we train different tasks on different data sets, and each time we train the model again and again for each separate task. Why not just train a model that is really great at understanding language, just as humans do? We don't learn each task separately as if we don't know the language at all. We learn the language first, and then we adapt to simple tasks by showing us, a few number of examples. So what they did in BERT is they invented a self-supervised learning task, which is masked language modeling. Masked language modeling is a task of hiding some words in the text and having the model complete them, under the assumption that the model that knows how to complete words well in a sentence really understands the language. And what they were able to show is the remarkable ability to do fine-tuning on unseen tasks. So this model actually understands language and can generalize from one task to many other tasks pretty easily, which is the holy grail of data scientists, because for most tasks we don't have good data sets that actually cover the entire information. So then researchers in Vision say, hey, these transformers look kind of awesome, right? Why do they enjoy them and we don't get to have them? So in 2020, which is merely 1 year ago, the Vision transformer takes the vision world by storm. It proposes a very simple attention mechanism that is, again, based on self-attention. And actually, previous speakers have already elaborated on that, so I'll just skip this. So transformers have taken the world of vision by storm as well. Merely 1 year since the Vision transformer has been published, we see so many papers covering so many tasks across vision. So we have the Vision transformer and then data-efficient Vision transformer, which trains the Vision transformer more effectively. CLIP, which we will touch on later in the lecture. DTR, as Yoli mentioned, that does object detection. Swing transformers. Dino, that does self-supervision. Bait, that does self-supervision. And one of my favorites is DALL-E, that you see here. It generates images by a text prompt. So the text prompt that we see here is an emoji of a baby penguin wearing a blue hat, red gloves, green shirt, and yellow pants. And I think the diversity and the abilities that the model shows to generate images that don't actually exist is amazing. So transformers have really revolutionized vision as well. So now that we know why we care about transformers, what is explainability and why do we care about explainability? We use deep neural networks in our everyday life all the time, and actually for really crucial tasks, say law enforcement, medicine, social networks, and banking. But these deep neural networks contain many biases, right? We train these huge models with sometimes trillions of parameters, and we have no idea what the model actually learns. And for example, GPT-3 has been shown to be both racist and misogynistic. So really properties that we wouldn't want to rely on for such crucial tasks. So explainability is a field of research that is aimed at revealing the logic behind this amazing black box of deep neural networks. So one of the goals is obviously to instill trust in us, the users, so that we know that we can trust the models that we're using for such crucial tasks. But also, it helps us in detecting the biases of the model and then maybe training it better to mitigate the biases, and reveals the logic behind the decision-making process of this black box that is a deep neural network. So let's dive into the topic of this specific lecture, transformer explainability. So we spoke about this simple, very intuitive attention mechanism. So is attention also an explanation? And this was the first question that researchers have asked in this field. Why can it be an explanation? Let's first explore that. We know that transformers do classification using a classification token. A classification token is simply another token that is appended to the set of tokens that the model gets. And this classification token is the only token that actually influences the output of the model. So if we have these attention scores that, as we said, are similarity scores, the attention scores with regard to the classification token should actually symbolize how much each token influenced the classification. So let's just look at the attention maps, these similarity scores for the classification tokens row. And these are our explainability scores, right? That's simple. Maybe it's self-explanatory. So as everything good in research, we have two papers, one claiming that attention is not an explanation, which got to NUCCLE 2019, and one is saying that attention is not an explanation, which got to EMNLP 2019. So researchers are really, pondering about this question. Is it an explanation? Is it not an explanation? And what are these attention weights anyway? What we're saying in our two papers is that attention maps can be used as explanations under two caveats. The first one is that, as Yoli mentioned, we don't have one attention head. We have multiple attention heads. And if we consider, for example, a vision transformer, each attention head can have a different purpose, a different meaning. For example, one attention head can be in charge of showing backgrounds, which is not always relevant to the classification. So simply averaging across the heads is kind of simplistic, right? The second thing is that we have multiple attention layers. When we have multiple attention layers, and we speak of token T1 in attention layer number 2, token T1 doesn't only represent token T1. It's token T1 that got information from other tokens. So what is the meaning of token T1 after 3, 5, or 12 attention layers? The tokens are mixed, and the meaning is very unclear. So preceding our paper, there was one paper trying to explain self-attention, which was published in ACL 2020. And they solved those two problems in the most simplistic way we can think of. They solved the multi-head problem by aggregating over the heads using a simple average. And they aggregate across attention layers using matrix multiplication. So really, basically, the most simple solution we can think of. But as you see here on the right, this image is actually taken from our paper. The method doesn't really work well. You have the peacock in the top image, and the heat map really doesn't correspond to the peacock. The second heat map doesn't correspond to the fish, and so on. They actually present another method that is based on a max flow problem in the attention graph, but I'm not going to get into it because it's inefficient computationally. So this is where we come in with our CVPR method. what we were saying is, those assumptions were good and they were fine, and we do believe that attention weights can be an explanation, but the assumptions made by the previous paper were a bit oversimplistic. So let's, solve them in a more sophisticated way. First, we say that regarding only the attention weights is a bit oversimplistic, and the transformer has many more layers other than the attention layers. So we use LRP, which is a relevance propagation method that is very common to explainability literature. And this relevance propagation ensures us that we are taking all layers into account. And then in order to average across the attention heads, we use gradients, which is also a very common use in explainability literature. And what gradients promise us, as we will see in the next slide, is a class-specific signal. So what do I mean by class-specific signal? Our method is the last method, the last column that you see here. If you have two objects in an image, say a dog and a cat, our method is able to output heat maps for each class you'd want to visualize. Our method was also used for sentiment analysis in NLP pretty successfully. But what I really wanted to focus on is to show you that explainability isn't just heat maps. It's also used for real use cases that really affect our lives. So if you look at the left images here, explainability can be used for detections of diseases. And actually, medicine is a field that uses explainability quite heavily. So as you can see, explainability is able to explain to us why a model classifies one X-ray image of lungs as a bacterial infection and another as COVID infection, actually showing us what in the lungs indicates a bacterial infection versus COVID infection. The middle figure here is detection of expressions. This paper did detection of expressions using transformers, and they use explainability to explain why the model detects some expressions over others. So if we look at the first row here, the last column is the method proposed by the paper, we can see that the person is frowning, indicating that he is angry, probably. And in the last row, we can see that the woman is surprised, and their method is focusing on both the eyes and the mouth. So the explainability really shows us why the models classify what they classify. And the last use is one of my favorites. It's facial recognition anti-spoofing. We all use facial recognitions on our phones, and it is important to make sure that the networks that actually do the facial recognition are not, prone to frauds. Say, if I wanted to make the facial recognition software think I'm Donald Trump, I could use a paper mask with the face of Donald Trump, and if the facial recognition software isn't that good, it would open Donald Trump's iPhone. So this paper actually uses transformers to detect frauds in facial recognition. So as you can see, their network detects the heavy makeup in the upper image, the tattoo in the middle image, and the paper mask in the bottom image. So this was all well and good for self-attention, but as Yoli said, we also use cross-attention and encoder-decoders for transformers. So in ICCV 21, we expanded our CVPR method to deal with other forms of attention other than self-attention. The first application that we show is for a clip. For those of you who know it, it's a very prominent model right now, and it's being used for guiding generative networks from StyleGAN to VQGAN to every generative network you can think of. And we show that clip actually knows to relate the text to the specific pixels in the image that are corresponding to that text. So for the text an elephant, you can see that the heat map really captures only the elephant and leaves the other objects away. For the zebra, you can see that the heat map really corresponds to the zebra. And for the lake, the heat map corresponds to the lake. So the model actually knows how to relate the specific text to the specific pixels in the image. The next thing we did was say, you know what, let's get out of the box. Let's stop with the heat maps and see if we can use explainability for a more interesting, more intriguing application. So we took DETR, which is a model that only does object detection. And we use the heat maps that we got from the explainability as semantic segmentation. So what we created is really a model which is weakly supervised semantic segmentation. And we show that explainability is able to produce really not that bad semantic segmentations, and that specifically our method was able to produce great heat maps which correspond to great semantic segmentation. If any of you is in the NLP field, then you know visual question answering is one of the most challenging tasks, because when you give a visual question answering model only the text, it sometimes gets the answers right. And I've actually tried some of the VQA models get a 40% accuracy with only text and no image, meaning you can't really know if the model really understands the question and the image, or if it just guesses the answer from the text. So what we show is specifically here for LXMERT, that the model actually can relate the words and the tokens in the input question to the relevant regions in the image. So the question here is, did he catch the ball? And the model actually focuses on the hand of the player catching the ball. So I was very happy to speak to you today, and I'd love to hear questions also via email if you have them. Thank you.
Thank you, Hila. I think that probably there are some questions. Actually, we need to proceed. We actually have one more speaker that wasn't in the program. So probably we'll proceed.